Mathematical decision making, network models, graph coloring for solving problems, Lesson 6, Ford Meadow. The learning goals for this lesson are for you to use vertex coloring with vertex edge graphs to solve problems to avoid conflicts, and to understand the basic steps of modeling and solving conflict problems using vertex edge graphs. We're going to start with a brain activator. Look at the graph at the right. Decide, does it have an Euler path? And explain. Does it have an Euler circuit? And explain your answer. You may want to pause the video. Let's do a quick check. Does the graph have an Euler path? Yes, it has exactly two vertices with odd valence. The other vertices have an even valence. Does it have an Euler circuit? No, the valences of the vertices are not all even. You have learned about vertex edge graphs. You use these graphs to model and solve problems related to paths and circuits. They can also be used to solve many other types of problems. In this lesson, you will investigate how graphs can be used to avoid possible conflict among a finite number of objects, people, or other things. To begin, consider the problem of assigning radio frequencies to stations serving the same region. In cities and towns, you can listen to many different radio stations. Each radio station has its own transmitter that broadcasts on a particular channel or frequency. The Federal Communications Commission, also called the FCC, assigns the frequencies to the radio stations. The frequencies are assigned so that no two stations interfere with each other. Otherwise, you might tune in to Rock 101.7 and get Mozart instead. Suppose 7 new radio stations have applied for permits to start broadcasting in the same region of the country. Some stations may interfere with each other, others may not. Suppose the 7 new radio stations that have applied for broadcast permits are located as shown on the grid here. A side of each small square on the grid represents 100 miles. The FCC wants to assign a frequency to each station so that no two stations interfere with each other. The FCC also wants to assign the fewest possible number of new frequencies. Suppose that because of geographic conditions and the strength of each station's transmitter, the FCC determines that stations within 500 miles of each other will not interfere with each other. Your work on the problems of this investigation will help you answer the question, how can vertex edge graphs be used to assign frequencies to these 7 radio stations so that as few frequencies as possible are used and none of the stations interfere with each other? For a small problem like this, you could solve it by trial and error. However, a more systematic method is needed for more complicated situations. Working on your own, begin modeling this problem with a graph. Remember, to model a problem with a graph, you must first decide what the vertices and edges represent. What should the vertices represent? Notice that on the grid, the vertices are already shown for us. Each of those vertices represents a radio station, one of the 7 radio stations that have applied for permits to start broadcasting in the same region of the country. So the vertices represent the radio stations. How will you decide whether or not to connect two vertices with an edge? Remember that the FCC determines that stations within 500 miles of each other will not interfere with each other. We can use that information to help us decide whether or not to connect two vertices with an edge. So it will be based on the distance they are apart. Now recall that for some it's going to be very easy, because if they're on a vertical line or a horizontal line, then it's just a matter of counting how many blocks apart they are. Each of those blocks is 100 miles. So this would be 100, 200, 300, 400. So radio station T and U are less than 500 miles apart. Similarly, when we look at two vertices that are on the same vertical line, we can count the units to see how far apart they are. So in this case, we know that radio station U and X are 400 miles apart. So again, they're less than the 500 miles. Now, when we look at Y and X, for instance, we're not going to count along the horizontal and the vertical to find their distance, because really the distance is this straight line segment. But notice that if you draw all three of those segments, the horizontal, the vertical, and the diagonal, then you have a right triangle. And if you'll recall, you can find the hypotenuse of a right triangle if you know each of the legs. So this leg would be 3 units, or 300 miles, and this leg is 2 units, or 200 miles. And so you can put that into the Pythagorean theorem to determine the distance that X and Y are apart. Make a decision for each of these to determine which of the vertices are within 500 miles of each other. Draw a graph of the problem. You have a worksheet to practice on these problems as we go through them today. This grid is on your worksheet, and you have space there to begin working. Pause the video. Resume it when you're ready to go on. Compare your graph to the one that I drew. What do the vertices represent in this model of the problem? The vertices represent the 7 radio stations. What do the edges represent? The edges represent the connection between 2 radio stations that are less than 500 miles apart. Your graph may not have looked exactly like mine, but it should have had the same valence for each of the vertices. Take a moment to check to make sure that each of your vertices has the same valence as the vertices in my graph. You may want to pause the video. Take a look at this graph. Does this graph also model the radio station situation? Check out the valences of the vertices. Are they the same as the valences of the vertices in your graph and in the graph that I drew? The valences are the same. T has a valence of 1, U has a valence of 4, V has a valence of 2, W has a valence of 3, X has a valence of 4, Y has a valence of 1, and Z has a valence of 1. That should be what you had on your graph, and that is what I had on my graph in the previous slide. 2 graphs can be the same even if their appearances are different when modeling a problem. Remember that the problem is to assign frequencies so that there will be no interference between radio stations. So far, your graph models this problem as follows. Vertices represent the radio stations, Two vertices are connected by an edge if the corresponding radio stations are within 500 miles of each other. Here's the last step in building the graph model. Represent the frequencies as colors. So now, assigning frequencies to radio stations means to assign colors to the vertices. Let's look at some statements in this table about stations and frequencies, and statements about vertices and colors. As we see a statement about stations and frequencies, we're going to transform that into a statement about vertices and colors. Two stations have different frequencies means that two vertices have different colors. Find a way to assign frequencies so that stations within 500 miles of each other get different frequencies translates into find a way to color vertices so that no two connected vertices are the same color. Use the fewest number of frequencies translates into use the fewest number of colors. Now use as few colors as possible to color the graph for the radio station problem. That is, assign a color to each vertex so that any two vertices that are connected by an edge have different colors. You can use colored pencils or just the names of some colors to do the coloring. Color or write a color code next to each vertex. Try to use the smallest number of colors possible. Pause the video. Compare your coloring to the one on the slide. You may not have chosen the same colors that I did, but your representation should satisfy the condition that vertices connected by an edge have different colors. So look at T and U, U and V, V and W, U and W, W and X, U and X, X and Y, and X and Z to verify that each pair has a different color. Notice that in this instance, the minimum number of colors is 3. Recall that this graph was also a representation of the radio station problem. Use as few colors as possible to color this particular model. Use colored pencils or write a color by each vertex. Pause the video while you work. How does your solution compare to the one shown here? Check each of your edges to make sure that the vertices on those edges are colored with a different color. Now, how does this help us to answer the problem that we were given initially? That is, we were looking to see the minimum number of frequencies that the FCC could assign to these 7 radio stations. We know that the minimum number of colors that we could use for this graph is 3. Therefore, the minimum number of frequencies that could be assigned to these 7 radio stations is 3. The radio stations that are colored with the same color would be given the same frequency. Your graph may have different colors than mine, but it would be a solution nonetheless as long as no two vertices on an edge have the same color. Now that you know about how to color a graph, you can use graph coloring to solve many other types of problems. As you work on the problems in this investigation, look for answers to this question. What are the basic steps of modeling and solving conflict problems using vertex edge graphs? There are 6 clubs at King High School that want to meet once a week for 1 hour right after school lets out. The problem is that several students belong to more than one of the clubs, so not all the clubs can meet on the same day. Also, the school wants to schedule as few days per week for after-school club meetings as possible. This table shows the list of clubs and the club members who also belong to more than one club. Your goal is to assign a meeting day, Monday through Friday, to each club. Remember, no 2 clubs that share a member meet on the same day. Use as few days as possible. We're going to solve this problem by graph coloring. First, we have to decide what the vertices are going to represent. This problem deals with different clubs at a school and the students who belong to more than one club. So looking at the information that's given, let's let the clubs be represented by the vertices. Conveniently, each of these clubs begins with a different letter of the alphabet. So I'm going to use those initials to label the vertices for our graph. Next, we have to decide what the edges will represent. We know the students belong to more than one club, so let's connect the clubs that share members. Looking first of all at the varsity club, we see Christina is the first student listed. Christina also is a member of the math club, so we must connect those with an edge. Then Shonda is a member of the varsity club. She's also in the French club and the computer club and the art club, so we're going to connect those vertices to F as well, to V as well. Then Carlos is another member of the varsity club. Carlos is in the math club. We've already taken care of that. And he's in the drama club, so we're going to connect the varsity club to the drama club. Moving down the list, we've already worked with Christina and Carlos in the math club. Wendy is a different student than we've seen before. She's also in the drama club. So the math club and the drama club will need to be connected. In the French club, we have Shonda. We've already worked with Shonda. So we're going to move down to the drama club. Carlos is the first student listed there, and we know we've already worked with him. Vic is a different student than we've seen before. So let's see where else he's a member. He's a member of the computer club. That means the drama club and the computer club need to be connected. And then the next student in the drama club is Wendy. We've already worked with Wendy. And moving down the list, we see that we've already taken care of these students as well. This graph then represents the problem. We have our clubs represented by the vertices, and then the connections between the vertices means that these clubs share a member in common. At least one, maybe several. Next, we need to decide how we're going to color the vertices, because remember, we want to have the fewest colors possible. Where would be a good place to start? I would choose vertex V. The reason I would choose that vertex is because it has the highest valence. As I look at this particular problem, V has a total of 5 vertices that are connected to it, edges that are connected to it, and so I'm going to color it, and I just chose red. Doesn't matter, but I know that every edge that joins at V, the other vertex of that edge will have to be a different color. All right, next, I want to be very strategic about solving this. So I'm going to look to see, well, which other vertex is connected to the most of the other vertices. And as I check that out, I can tell that it has to be D, because D has a valence of 3. So V is connected to D. So I am going to have to color D a different color than I'd colored V. Now, the other vertices that fall into line as far as valence is concerned would be M and C, and they're both connected to D and to V, and so that means I'm going to have to color those in a different way. Notice I also could color F the same color, because M is not connected to F, C is not connected to F. And I could even color A the same color, or I could color A purple. It doesn't make any difference. Once you have the colors listed here, you can assign those colors to a day of the week. So for instance, red could be Monday, the aqua color could be Tuesday, and then the purple on Thursday. We usually don't schedule meetings on Wednesdays because we have faculty meetings and things like that. So this is one solution to the problem. The minimum number of days it's going to be necessary to schedule club meetings and not have conflicts with scheduling for students who belong to more than one club is 3. So we'll need 3 days of the week to schedule those. Another class of problems for which graph coloring is useful involves coloring maps. You may have noticed in your geography or social studies course that maps are always colored so that neighboring countries do not have the same color. This is done so that the countries are easily distinguished and don't blend into each other. In the following problems, you will explore the number of different colors necessary to color any map in such a way that no two countries that share a border have the same color. This is a problem that mathematicians worked on for many years, resulting in a lot of new and useful mathematics. For this problem, countries are assumed to be regions that are contiguous, not broken up into separate parts, and border means a common boundary of some length. The touching points don't matter. Shown here is an uncolored map of a portion of southern Africa. Using a copy of this map on your handout, color the maps so that no two countries that share a border have the same color. Remember that you can write the colors in, or you can actually use colored pencils. First of all, as we begin to draw the graph for this, we need to look at what the vertices are going to represent, and in this case the vertices are representing the countries. I have labeled the vertices using the first letter of the country, unless the country had an initial that was shared with another country. In that case, I used the first 2 letters. The edges now are going to represent the shared border. So all of the countries that share a border are going to be connected with an edge. And I tend to move from the top left and go in a clockwise rotation. So I've done the Democratic Republic of Congo and indicated the countries that share a border with it. Now moving to Tanzania, we see the connections there. Malawi, Mozambique, Zimbabwe, Botswana, Namibia, and Angola. And once I get to Zambia in the center there, it has already been connected to all of the countries that share a border with it. So this graph represents the map. Now we have to decide about the coloring. And if you recall, in that last problem, we started with the vertex having the greatest valence. So let's figure out what the valence of each of the vertices is. And as we look at it, we want to sort that. So it makes sense for us to start with Zambia. Once you've colored Zambia, then you can decide the colors that you're going to use for the others. Pause the video and complete the color assignment and then color your map. How does your map compare to mine? Remember that you may not have the same colors, may not have used the same coloring scheme, but no two countries that share a border should also be painted the same color. So hopefully you were able to do this and had a minimum of 4 colors. So we want to use the least number of colors possible. Now, what we've been using actually is the Welsh-Powell algorithm, and these are the steps for the algorithm. Make a list of all the vertices, starting with the ones with the highest degree and ending with those of lowest degree. Then color the first uncolored vertex on your list with an unused color. Now, initially, they're all going to be uncolored vertices. Even though my vertices have been shown in black, we're considering black not to be a color. We're going to use brighter colors for these. So we're going to color the first uncolored vertex with a color, and then go down the list coloring as many uncolored vertices with the current color as you can, following the rule that vertices connected by an edge must have different colors. If all the vertices are now colored, you're done. If not, then you go back to step 2. So you'd already colored the first one on your list. You may have colored the second one or not, but whichever one is not marked off, you want to color it with a different color. And then continue with this process. In the last problem, you found the fewest number of colors needed to color the Africa map. Now think about the fewest number of colors needed to color any map. This map is colored with 5 different colors. Use the algorithm to see if you can color the map with fewer than 5 colors. We're going to use this algorithm as we determine the fewest number of colors that we can use to color this particular map. The map is on your handout. Work along with me as we move through this problem. First of all, let's go ahead and label the regions. The vertices of our graph would represent the regions of the map. Next, in our algorithm, we're to find the valences of the vertices. We know that A has a valence of 3 because A borders on 3 regions, B, H, and G. B also has a valence of 3 because it borders on 3 regions, A, H, and C, and so on. It turns out that H has the highest valence. So we want to sort these vertices in order based on the highest valence to the lowest. Here I've sorted, and notice that for some vertices they have the same valence. I just put those in alphabetic order. There's no priority really to those. It just is my way of staying organized. So the first thing we're going to do is pick a color for the region labeled H. And once I've done that, I'm going to check it off. Now I move down my list in order because I want to be sure to color every region possible the same color as I colored region H. So the next one is C. Notice that region C borders on H, so I can't color it red. Moving down, E. E also borders on H, so it can't be red. I check A, B, F, and G, and all of those regions border on H. None of them can be colored red. Now when I get to the bottom of my list, D is a region that doesn't border H, so it can have the same color. Now I have two of my regions checked off. The algorithm says that if you get to the bottom and all of them are done, then you're finished. If not, go back to step 2. And step 2 says to start with the top one that hasn't been colored and color it with a new color. So our top one that hasn't been colored is C. So we're going to color C a different color, and notice that I've marked it off, checked it off. Moving down, E borders C, so I can't color it green. The next one is A. A doesn't border, so I can color it green also. Moving on down, I can't color B green because it borders C and also A. I could color F, however, because it borders neither of those. But then when I get to G, notice that it borders both A and F, which have been colored green. So I've gotten to the bottom. I'm not finished, so I have to go back to the first uncolored vertex, which in this case would be E. So E is going to be a different color from red or green. So let's color it blue and check it off. Then moving to B. B can be blue because it doesn't border any region colored blue. Check that off. And finally G. So as I look at G, it can also be colored blue. Now we're down at the bottom. All of the regions have been colored, and we have been able to do this using the algorithm, and we find that the least number of colors that we can use to color this particular map is 3. Alright, in this lesson you've learned to use vertex coloring with vertex edge graphs to solve problems that could have conflicts, such as conflicts in scheduling, conflicts as far as the frequency of radio waves is concerned, conflicts as far as just coloring a map, because you want to let every state or country or region stand out and not blend in with its neighbors. And you've also learned an understanding of the basic steps of modeling and solving conflict problems using vertex edge graphs. Now you're going to work on some practice problems that will further your understanding of solving these problems by modeling with vertex edge graphs and with coloring. If you need to refer back to the video, you may do so at any time.